Let's finish up the chapter 22 practice problems. Number 12, the current in an inductor lags the voltage. This lag is caused by what? So this is talking about how the current and the voltage are not in phase in your circuit. So you know that in an AC circuit that the current looks like this. It's oscillating as a function of time, and the voltage also oscillates as a function of time, but they don't reach their maximum at the same time. They're out of phase. So this lag, why this happens is because of the back EMF in the coil. So what happens in your AC circuit when you have an inductor is that all I need to do is draw an inductor. I don't have to draw everything here. But if you just show an inductor and a battery, all right, so when you close the switch, so current can flow here. Well, as soon as current is flowing here, we have a huge change in magnetic flux, because at first there was no current here, no magnetic field. As soon as you close that switch, there's a magnetic field here. So what that means is that as soon as you close the switch, there's a very big back EMF induced here, right? That is given by the previous equation that we just looked at, that depends on the inductance of that coil and how fast the current is changing. But it turns out that at the beginning is basically the EMF of the source. That's how big the voltage is. You have a very high voltage here. And that prevents the current from flowing like it wants to. So that's why the current is lagging the voltage. Number 13. What is the RMS value for a current with an amplitude of 10 amps? So an amplitude of 10 amps means that's the maximum value here is 10. But that's not the RMS value. So this is a plug and chug to realize that the RMS value is given by that maximum value divided by the square root of 2. That's how we define the RMS value. So do 10 divided by the square root of 2, and we're going to get 7.1 amps. And the RMS value is always going to be smaller than the maximum value, right? The whole purpose of the RMS value is that if you just looked at the average value of this current, it would be 0, because it goes up and down. It's negative 10, a lot of times it's positive 10. The average value of this current would be 0. The average is not a very useful value, but the RMS value is actually a number that can tell you about what's the actual, how does the current actually vary with time here. Number 14, so this is, you've got a resistor, an inductor, and a capacitor. So this is an RLC circuit, and we are given the RMS current, IRMS. Find the RMS voltage across the resistor. So I do have a little typo because I only have one answer choice here, but to find the RMS voltage across the resistor, that would just be the current times the resistance. So that would be 3 times 50, and that would be 150. So that would be that choice. Across the inductor, what you're going to do is it's going to be the IRMS times the inductive reactance. And to find the inductive reactance, you have to use 2 pi f times L. So the frequency is the 60 hertz here, and we have the 0.1 henries. So you put in those numbers in here, the 0.1 and the 60 and a 2 pi, you're going to get 37.7 ohms for the inductive reactance. You multiply that one by 3, and that's the one that gives you the 113. So I meant to erase this part and this part of the question for these particular choices. And number 15, this is one that tests your algebra skills. We have your RLC circuit here, and we're given the frequency. This is an AC circuit, and what should be the capacitance? A variable capacitor means you can choose it to be what capacitance that you want. And you want to have resonance. That means you want to achieve the resonant frequency, which is given by 1 over 2 pi square root of LC. So you have to manipulate this equation to solve for C. So what you do is you multiply everything by square root of LC, and you divide everything by the frequency. That's the first step. And then you are going to square both sides. LC equals 1 over 2 squared pi squared f squared. And then you're going to divide by L. So divide by L, divide by L. So then you have to plug in all the numbers in here. 1 divided by 4 pi squared. F, the frequency that you want is the frequency, you want the resonant frequency to match the frequency of your circuit. So this is the resonant frequency that you're trying to get. And the L goes in here. So you don't even care about the value of the resistance. You plug all those numbers in, and you'll get 3.4 times 10 to the negative 6 farads.